Recently, almost all the attention in the optical communications world has been on CPO. After Computex, the market's expectations for NVIDIA's silicon photonics switch entering mass production heated up. Everyone is discussing the same thing: how to move the optical engine right next to the chip to eliminate the power consumption of that long electrical channel. In the exact same week, on June 14th, Google posted a paper on AR14. The authors include Norman Juppy and David Patterson, and the title is refreshingly understated. From TPU v2 to Ironwood: 5 Generations of Training Supercomputers. It will be published in the July/August issue of IEEE Micro. This paper, using 8 years, 5 chip generations, and longitudinal data showing a roughly 3600x increase in overall supercomputer performance, thoroughly explains another optical path that has been overshadowed by the CPO hype: OCS. The all-optical circuit switch. One thing worth noting is that the paper talks about OCS on a completely different channel from the market. The market cares about how to save optical power right next to the chip, whereas the paper cares about whether a system composed of thousands or tens of thousands of chips can survive, and whether it can be scheduled. In its eyes, OCS is not just another power-saving optical component. It is a system capability. Precisely because of this, it is not even on the same layer as the CPO everyone is talking about. One handles topology, the other handles the port. This judgment is not a fleeting opinion. The paper carries OCS all the way from TPU v4 to the present day, and in its conclusion, lists it as one of the only 2 unique TPU designs not followed by others. This amounts to using 8 years of longitudinal data to stamp a seal of approval on OCS's value that lets first feel the scale of these 8 years. From TPU v2 in 2017 to Ironwood in 2025, the peak performance of a full supercomputer has grown about 3,600 times. The most intuitive reflection of this is the shared memory pool. The directly addressable HBM across all chips in a pod grew from 4 terabytes in TPU v2 to 1.77 PB in Ironwood. Roughly a 400-fold increase. Single chip performance, HBM capacity, and bandwidth each went up by 1 to 2 orders of magnitude, which I won't spell out here. But the paper's focus is not on numbers getting bigger. It's on which designs held up over 8 years. During these 8 years, the dominant deep learning workloads changed several times. Transformers and diffusion models rose to prominence one after another, yet TPU's basic architecture remained stable. Compiler and software stack optimizations from earlier generations could be directly reused for new ones. The paper even puts architectural stability first in its title. This contrast, workloads changing fast, the underlying architecture barely moving, is laid out bluntly in the paper's very first figure. In its closing words, the paper takes a string of key design choices made in the early days of the TPU and checks them against today, including systolic arrays, narrow-width floating point, BF16/FP8, using HBM as main memory, custom high-speed inter-chip interconnects, and direct software-managed on-chip memory. All of these have since been successively adopted by other AI accelerators, retrospectively proving those initial choices right. The authors even go as far as putting it in the same sentence as the IBM 360 and x86. They hope this architecture, born for AI, will still be in use decades from now. Beyond this list of verified by peers designs, The paper leaves one sentence that the optical communications community should pay even more attention to. To the author's knowledge, there are still two innovations unique to TPU that others haven't followed, namely the OCS all-optical circuit switch and the SparseCore for sparse embeddings. In other words, OCS is not a temporary solution for one generation. It is one of the very few things Google has kept and reused over 8 years, and that almost no peer has been able to copy to this day. In this piece, we will only analyze the OCS part. It happens to be exactly the thread that was overshadowed by the CPO craze this week, yet was revalidated with long-term data by this paper. Let's first sort out the hierarchy clearly. Above the chip sits a CPU host housing 4 chips. 64 chips form a cube. Many cubes combine into a pod. And OCS sits between cube and cube. In other words, CPO handles the side of the chip ports, and OCS handles the side of how cubes connect to each other. OCS first entered the TPU supercomputer in 2021 with TPU v4, which was the first supercomputer in history to use an all-optical circuit switch. Its position must be clarified first. OCS is a physical layer beneath the ICI. ICI is TPU's custom interchip interconnect, forming a 3D torus network via routers built into each chip. OCS sits underneath it, and its role is to bypass failed nodes when hardware malfunctions, and to reassemble the 3D torus topology. This 5th-generation review paper from June 14th essentially rediscusses this design, which has been in use since V4, within the overall evolution of the TPU. Physical media is used based on distance. Inside a single rack, electrical connections, copper, offer the best cost-performance ratio. Crossing between racks is where optics comes into play. Google sets the basic unit of cabled interconnection as a cube of 4 times 4 times 4 is equal to 64 chips. Within a cube, copper is used. Between cubes, optics is used. A cube has 6 faces, each with 16 optical links, totaling 96 links connected to the OCS in the TPU v4 generation. A single OCS had 136 by 136 ports, 128 ports plus 8 spares for link testing and repair. The entire v4 pod used 48 OCS units, serving 64 cubes, to form an array of 4,096 chips. This includes the micromirror mechanism of OCS and the port count. And insertion loss specs of the commercially available Lumentum are 300. The method of optical links coming out of 6 cube faces, each connecting to OCS, is shown very clearly in Figure 4 of the paper. The left side shows a 4 by 4 by 4 cube, and the right side shows how it connects to rows of OCS along the X, Y, and Z directions. This all-optical switching layer brings 3 concrete benefits. Fault tolerance. An Ironwood supercomputer has 2,304 CPU hosts. Without OCS, host availability would need to exceed 99.9% to ensure a single slice does not lose compute power. With OCS, failed nodes can be bypassed, and defective units detected in the field can even be directly removed from production via OCS to be repaired at a convenient time. Scheduling in the early TPU v2 and v3 days. To schedule a 128-chip job, the scheduler had to physically find 128 contiguous idle chips. With OCS, it can pick 2 cubes from any location in the supercomputer and combine them. Ironwood deliberately made its pod size 9,216, a number that is not a power of 2, precisely to leave 16 spare cubes, so that even if some nodes go down, it can still run 4 2048 chip tasks concurrently at deployment. In the TPU v3 generation, the entire machine had to wait until all 1024 chips and cables were installed and tested before it could be used. A single lake component would hold up the whole site. From v4 onwards, each rack is independent, and a set of 64 chips can be put into production as soon as it is installed. The paper also provides a counterfactual piece of evidence showing that OCS is not just the icing on the cake. If OCS were not used, a completely different network topology would be required, the total cost of ownership would be higher, and spare chips plus independent cross-connect switches would need to be stuffed into each rack. This could eat up nearly half of a rack space, simultaneously amplifying the cooling problem. Ultimately, OCS solves the problem of a large system being able to reconfigure itself around failed nodes, job scheduling, and phased rollouts. Not making a single link faster. CPO's job is at the port layer. Look back at the endlessly discussed CPO. What co-packaged optics aims to do is move the optical engine next to the switch or compute chip and package them together, shortening the dozens of centimeters of high-speed electrical traces on the board to a small stretch near the package or substrate. This reduces the per-bit interconnect power consumption caused by those long electrical channels and pluggable optical modules, while freeing up ports for high-density switch ASICs. Note: CPO does not eliminate optical to electrical conversion. The conversion still has to happen. It's just moved right next to the ASIC. Its responsibility is the chip port layer. What this paper talks about is actually a completely different layer. From start to finish, it cares about how systems connect and survive, and hardly touches the CPO layer. This does not mean Google denies CPO. It's just that the two are not even addressing the same problem. Put them into a single sentence, and the dislocation becomes crystal clear. CPO allows the light in a fiber to enter and exit the chip more efficiently, while OCS allows the connections among thousands of fibers to be physically repatched. One manages the port, the other manages the topology, at least within the Google TPU architecture. They solve different bottlenecks and are not in a substitutional relationship. This is in line with how Google layers its networks by distance into intra-chip, intra-rack, intra-campus, and cross-data center, each running a different solution. The marginal cost structure of OCS also explains why Google has been willing to invest in proprietary development for 8 years. This all-optical switching layer has a characteristic. The physical medium itself does not need to be replaced when transitioning from one generation's data rate to the next. The cost amortization is also low. Google provided a figure in the 2023 TPU v4 paper. OCS plus the underlying optical components account for less than 5% of the total system cost, and less than 3% of the power consumption. IT is cheaper, more power efficient, and faster than the InfiniBand alternative compared in the paper. One more thing often gets calculated in reverse. The OCS itself does not perform optical to electrical conversion. IT is merely a set of angle tilting micromirrors that physically connect light paths directly. However, the two ends of the link still each carry transceivers and optical modules. Inserting an all-optical relay node in the middle of a link does not reduce the transceivers on the link ends. On the contrary, you have to hang an additional set on each side of the node. So, Google makes its own OCS, does not equal the demand for optical modules gets slashed. The division of labor between the two optical paths is actually very clear. Put this week's two topics side by side in a table, and who manages which layer becomes clear at a glance. Next time you see a news article or analyst report about CPO or OCS, first ask whether it is talking about chip port power consumption and density or topology reconfiguration between racks. Distinguish this, and most of the confusion vanishes. The threads worth continuously watching from here can be boiled down to three categories. The one most worth focusing on is whether the industry truly starts to spill out beyond Google. Whether commercial OCS manufacturers can secure volume production orders from cloud providers outside the Google ecosystem says more than any port count number about whether this path has broken out of a single company. Axlink is not moving slowly here. It showcased a complete MEMS all-optical switch at OFC 2024, and at OFC 2026, it pushed its OCS solution further into cluster interconnect scenarios. Another signal of the same kind is whether the port specification of the Apollo OCS will move up from 136x 136. That is how you see if this proprietary line is still iterating. And the answer has to wait for Google's next optical switching paper. The second category is whether the relationship between the two layers gets further solidified. If Google won. Day also uses NPO or CPO on the switch's access side. Note, the access side, not the OCS layer. That would precisely prove that the port side and topology side are complementary and separate, not one replacing the other. The longer-term, fundamental variable lies in workload patterns. As all-to-all communication-intensive models, like Mixture of Experts, MO, become more mainstream, the value of dynamically reconfigurable topology will only be higher than it is now. This is the underpinning of the long-term demand for the OCS path. The third category is supply chain resilience. When it gets down to components, it's about the localization progress of key parts like MEMS optical switches, circulators, and wavelength division multiplexing, which determines how far this path can be replicated within China. What should have been watched this week was never just the half of the story about stuffing light into the package. The OCS path does not get as much screen time as CPO, but Google, with 8 years and 5 generations of data, has listed it among those two unique designs no one has been able to copy yet, and placed it squarely at the position of whether the system can actually run. One handles the port, the other handles the topology. TOCAI optical interconnects clearly. You have to keep both eyes open.